Your phone battery can both discharge and charge, two seemingly opposite processes. How is it that the same device can do both? Even more amazing, when discharging, it's chemical energy to electrical energy. When charging, it's the reverse, electrical energy to chemical energy. Today, we use a copper-zinc cell visualization to reveal the secrets of the two-way conversion between galvanic and electrolytic cells. By the end of this 3-minute video, you will finally master the concepts of positive, negative, anode, and cathode that confuse so many students. First, let's build a classic copper-zinc galvanic cell. Left beaker, zinc strip in zinc sulfate solution. This is the negative electrode, anode. Right beaker, copper strip in copper sulfate solution. This is the positive electrode, cathode. Middle, a special bridge, the salt bridge, connecting the two beakers. Top, wires connecting the electrodes with a light bulb or voltmeter. The moment we connect it, the bulb lights up, the voltmeter jumps. This shows that the device is spontaneously generating current. But why? The answer lies in the difference in reactivity of the metals. Step 1, electrons depart. The active zinc atoms are eager to let go. They shed electrons, turning into zinc ions that dissolve into the water. These abandoned electrons have only one path, through the wire toward the copper electrode on the other side. Step 2, electrons arrive. Once the electrons reach the copper electrode, they don't stay idle. The copper ions in the solution are waiting in ambush. As soon as they receive electrons, they are reduced to copper atoms and deposit onto the surface of the copper electrode. Step 3, charge balance. Here's the problem. On the zinc side, zinc atoms are constantly becoming ions, so the positive charge increases. On the copper side, copper ions are being used up, so the positive charge decreases. Without charge balance, the current would stop instantly. This is where the salt bridge becomes the hero. The salt bridge is filled with a saturated ionic solution, usually KCl or KNO3. When the zinc side has too much positive charge, anions from the salt bridge move over to neutralize it. When the copper side lacks positive charge, cations from the salt bridge move over to replenish it. The salt bridge acts like an ion courier, ensuring both sides remain electrically balanced so the current can flow continuously. Let's summarize the essence of a galvanic cell. Negative electrode, zinc, loses electrons undergoing oxidation. Electrons flow out. Positive electrode, copper, gains electrons undergoing reduction. Electrons flow in. Salt bridge balances charge, maintaining the circuit. The two half reactions are split by the wire and salt bridge, forcing electrons to travel the external circuit. This forms the current. Galvanic cell, chemical energy to electrical energy, happens spontaneously. Up to now, the logic of the galvanic cell is clear. The active metal proactively gives away electrons, and the less active metal passively receives them. But what if we force the process in reverse? What happens if we replace the light bulb with an external power source? Now, remove the bulb and connect an external DC power source, like a charger. The moment the power is on, something magical happens. The side that was supposed to dissolve starts to deposit metal. The side that was supposed to deposit starts to dissolve instead. Everything is reversed. The external power source acts like a powerful electron pump. It pulls electrons away from one electron while pushing electrons into the other electron. It forcibly reverses the direction of electron flow. In an electrolytic cell, cathode connected to the negative terminal of the power source pumps electrons in, creating a high electron concentration. Cations in the solution, like Cu2+, are attracted here, gain electrons, and are reduced to solid metal. Anode connected to the positive terminal of the power source pulls electrons away, creating the electrode electron deficient. The electrode metal itself, or anions in the solution, are forced to lose electrons, undergoing oxidation. Mnemonic: galvanic, negative oxidation, positive reduction. Electrolytic, cathode reduction, anode oxidation. Now you should understand. Galvanic cell, chemical energy to electrical energy. Spontaneous, driven by reactivity difference. Used in batteries and fuel cells. Electrolytic cell, electrical energy to chemical energy. Non-spontaneous, requires external power. Driven by applied voltage. Used in electroplating, refining, and charging. The essence of charging, using the electrolytic mode to reverse the reaction that happened during discharge. Time for a quiz. When charging a lead-acid battery, does oxidation or reduction occur at the battery's positive terminal? Hint: charging is the electrolytic mode, and the positive terminal is connected to the positive terminal of the power source. Post your answer in the comments. From galvanic to electrolytic, from discharging to charging, two processes that seem opposite are both fundamentally redox reactions powered by different drivers. Galvanic cells rely on the natural potential of metal reactivity. Electrolytic cells rely on the artificial push of an external power source. In the next episode, we'll talk about electropotential, how to quantify this potential and predict the direction of reactions. Found this helpful? Give us a like and subscribe. See you next time.